Well, g'day. If you know anything about me, you've watched any of my videos, you know how much I love making things real. And so here it is, we've recreated the question. We've got an electric motor here. Of course, motors, DC motors are also generators. A quick little 3D printed up pulley there. And the thread, you won't be able to see it on camera. It's really, really fine. It's a fine nylon thread. You buy it in a bobbin. It's the kind of thing you can put into your sewing machine if you want to sew something up with nylon to kind of make it really, really strong. And here's my hanging mass there ready to go. Also got a switch wired up through heavy gauge wire. Don't use light gauge wire. Use wire that can cope with at least 10 amps. Otherwise, there's too much resistance in it and you won't see as much electromagnetic braking. And I've got a switch here. So in the up position, the switch is closed. And so the current can flow and you'd expect to see electromagnetic braking. With the switch in that position, it's an open circuit, that's kind of the free fall position. So while there will be an induced EMF, the motor will act as a generator. Because there's no closed circuit, no current will flow, therefore there'll be no generation of flux to oppose the original change in flux, hence no electromagnetic braking. All right, let's give it a go. We're gonna start with it in free fall mode first. You'll be able to see when I switch it across. Here we go. Quite a dramatic difference between electromagnetic braking and no electromagnetic braking. We want an evidence-based answer for what the velocity time graph looks like. So what are we going to do? Of course, we're going to take our data from that video, put it into Tracker, which is my favorite piece of free open source software. You put a video in, you pretty much tell it the shape you want it to track. As long as you've got lots of light, short shutter speed, a nice clean background, it does a pretty good job of tracking it. So let's track this thing as it's falling. The bottom graph here is our velocity time graph. And you can see in that moment of time, across that period of time there, a lovely kind of straight gradient downwards. A straight gradient downwards on a velocity time graph means it's accelerating in that kind of downwards direction. And so it's accelerating downwards. We've kind of called that a negative one because we've called up positive. The only force on that object is the weight force downwards, unopposed by anything else. And you can see, if I just back it up a frame or so, you can see that it's at around about, if you watch that little switch there, you can see it's around about that frame that the switch gets thrown. And so now a current can flow. Of course, there was always an induced EMF in the motor, but without a complete circuit, the current can't flow. Therefore, you don't get the generation of new flux opposing the original change in flux. I'm talking Lenz's law here, right? So remember Lenz's law, the bit between an induced EMF and a current should always be like, if a current can flow, it will give rise to blah, blah, blah. So now the current can flow. And we've got our weight force downwards, and now we've got this massive electromagnetic braking force upwards. The thing is traveling really, really fast. The rate of change of fluxes is very great, and so the ultimate size of that upwards electromagnetic braking force is massive. And so you can see over the next few frames that it's accelerating upwards, which means it's slowing down. It's getting a slower and slower velocity. So what's happening, because there's a net upwards force, it's slowing down, which means that the magnitude of the electromagnetic braking force is getting less, and so the net force is getting less, and there'll be a point where the net force is zero. Now, when I tracked it, there is actually a moment of time where it goes beyond zero velocity and actually has a slightly positive velocity. That's a bit of bounce on the stretch of that kind of nylon cord. But you can see very quickly after that, it settles down to this lovely constant velocity because now there is zero net force on it. The electromagnetic braking force is exactly the same as the weight force, no net force on it, therefore it's at a constant velocity. You can see a constant gradient here on our displacement time graph and a zero gradient here, constant as well, on our velocity time graph until watch when the switch gets opened again at this moment in time right there. Now the current's not flowing, it's in free fall, and you can see the thing falling. So the gradient here, well, you can see it's really, really close to the gradient there. It's pretty much the same gradient. In fact, if there's any difference, and there is a slight amount of difference in those gradients there, it's because early on there was more thread on that little pulley, and so it had a slightly larger diameter and a slightly smaller diameter after a fair bit of it unwound when he opened the switch again, and that probably would explain it. But nevertheless, you can clearly see the shape of the velocity time graph. But before I go, I want to explain to you why this is important. What are the real-world applications? Well, one of the most important real-world applications is becoming increasingly evident on our roads is in electric vehicles. So in an ICE, a petrol-powered or diesel-powered vehicle, when you want to slow down, what you do is you put your foot on the brake and it puts brake pads against this spinning rotor that's attached to the wheels, and you're effectively turning your kinetic energy into heat energy, which is then just dissipated into the environment, completely wasted. So when you think about it, every time you put your foot on your brake, you are basically wasting petrol, fuel that you spent money on to gain kinetic energy, and you're just turning it back into heat, and you're just kind of letting that go into the environment. With an electric vehicle, you've got that electric motor, so you can apply electromagnetic braking. And so in most electric vehicles, as you ease off the accelerator, it realizes you're going faster than you want to do. And so now the electric motor acts, just like in this experiment here, as a DC generator, and it puts that energy back into the battery. So in an electric vehicle, when you are braking, you're converting that kinetic energy back into chemical potential energy in the battery. That's why they are one of the reasons why they are so energy efficient, especially in stop-start driving in the city, because all of that energy that you would otherwise waste gets converted back into electrical energy, stored as chemical potential energy in the battery for later on. And here's another modern application. Electromagnetic braking using motors has probably got more of an application in modern days than in past days, but here is one of those applications. If you sat my Year 11 exam last year, you'll know about gravity batteries. There are actually real ones in the world, one in America, one in China. And the idea is you store electricity by using the motor to winch up large masses, 33 stories, several tons of each of those masses. And then when you want the electricity back to feed the grid, perhaps at night time, you let the battery fall, and you can see that a current flows and you get that energy back. They're actually reasonably energy efficient, returning energy efficiencies of greater than 90%, which is really comparable to batteries. Just junk concrete as your mass, so a lot less investment to build than a large battery bank.